This is the fifth and last part of Lecture 6 of Applied Machine Learning. In this video, we're going to look at multi-class classification. Previously, we saw an algorithm called logistic regression, which is an important and widely used algorithm for binary classification. And in this video, we're going to see how to extend logistic regression to an arbitrary number of classes k. Now, recall the model that we have defined earlier, logistic regression. In logistic regression, we assume that the function f that maps inputs x to targets y takes the following form, which is a transformation of a linear function of theta and x, and this transformation is the sigmoid function. Essentially, the sigmoid function takes a real number that's given by the dot product of theta and x, and it squeezes it such that it is between 0 and 1. And this is what this function does, and when we put it within this function f, we have the following form. So how can we extend this function to multi-class classification problem where we have an arbitrary number of classes k? Well, one simple approach that we could use, and this is an approach that is reasonably often used in practice and it can be applied to any machine learning algorithm. This approach consists in training one classifier against all the other classes. And we train one classifier per class to distinguish that class from all the other classes. It's called the one versus all approach. We, in fact, in a way did this in the previous video when we trained a binary classification model to predict setosa from non-setosa flowers. And similarly, we could have trained a model to, so let's say setosa was class 0 and the other two classes were 1 and 2. Well, we could have also trained a model to distinguish 1 from 0 and 2, and we could have trained a third model to distinguish class 2 from classes 0 and 1. And this would have given us a way of distinguishing the three classes. This approach works and is reasonably often used, but from a conceptual point of view, it is not fully satisfying and it's not entirely elegant, and in particular, it loses the valid probabilistic interpretation that we had earlier for the logistic regression algorithm. For some algorithms in machine learning, this one versus all approach is the best that we can do. But it turns out that in the case of logistic regression, we may fit a different model that is also going to be a probabilistic model that is a generalization of logistic regression and that directly outputs multi-class probabilities. As an example to illustrate this algorithm, we're going to again use our iris flower dataset. And here we're going to use the full version in which we have the three classes. Again, here each point is a flower for which we have different measurements, and we're showing these flowers in blue, light brown, and dark brown. These colors represent our three classes. In order to generalize our logistic regression algorithm to multiple classes, we're going to take a similar approach to the one that we took in the previous video. And our first approach is going to be to extend the logistic function. So you may recall that the logistic function, it was a mapping from the real numbers to the unit interval 0 and 1, and it can be seen as mapping each input z to a probability. We now want to generalize this to multiple classes. Therefore, we're going to define a multi-class extension, which I'm going to denote here with this extra arrow on top. Now this is the multi-class version, and now it maps a k-dimensional input into a k-dimensional vector of probabilities. So if we have k classes, we provide it with k inputs, and we have as an output k probabilities for this function. So how are we going to define this new multi-class extension? We're going to use the following expression, and this is something that is going to be called the softmax function. Essentially, the softmax function is, so as I mentioned, it's a vector valued function. It outputs a vector of k probabilities, and each component, denoted here by a lowercase k, has the following form. So here the kth component is, well, let's first define what this function does in 2 steps. First of all, this function looks at all the components of z, and it applies to them the exponential function. So we look at each component of the vector z, the input vector z, and we exponentiate it, which gives us this expression for the kth component. And this is useful because it makes z non-negative, and if we're going to be using probabilities, we need non-negative numbers. So now all the components of z are non-negative, and the remaining step we need to do to make it a probability is just to make sure that all the non-negative components sum to 1. And we do that by simply normalizing by the sum of the components. So again, here, in order to obtain this expression, we have exponentiated all the components of z, and then we have normalized all their components by their sum, such that the sum across all the components of this new vector sigma of z, such that the sum of these components equals to 1. This is called the softmax function. And there are also other ways of deriving this function, but this is an intuitive explanation for why it's reasonable. Let's now look at a special case of this function when k equals 2, and we have 2 classes. In this case, we have the following expression, where the first component of, so the probability of the first class has the following form. And now observe that this expression, it takes the same value if we multiply each z by some number. So if we were to multiply both the bottom and the top by an arbitrary scalar a, then we would still have the same distribution. We would simply rescale it. And since we're simply rescaling this this distribution, so in a sense it's over-parameterized. We have an extra parameter, right? If we were to multiply z by z1 and z2 by 2, we would still have the same set of probabilities. So in a sense we have an extra parameter. And in order to avoid this over-parameterization, we can arbitrarily set one of these probabilities to 1. So we can assume that the exponential of z1 equals 1. Or in other words, we can just divide on both sides by exponential of z1, and this will cancel off, this will cancel off, and we're going to have a different number. So here I should denote this z2 prime because this is a slightly different z2 from before. But essentially we can assume the following form, and as we go across all the values of z2, we're going to be able to express the same set of probabilities. So here I have just simplified this expression by setting z1 to be by setting z1 to 0 essentially arbitrarily, because z1 is an extra degree of freedom that we don't need. We just need z2, and this will be enough to define all the possible probabilities for the 2 classes. And now you can see that this form is really similar to what we had before for the logistic function, except that we don't have the minus here. But even if we had the minus, it doesn't change because this is an arbitrary input. So it doesn't really change the set of, it's essentially just flipping the function. It doesn't really change much. And we could use this function also as our probability. We could use this instead of the logistic function equally well. And this shows that the softmax is essentially a generalization of the sigmoid function. So now let's use the sigmoid function to define a model that we can use in k-class classification. Recall that in the binary classification setting, we assumed the following form, where we had weights and features, and we would map their dot product into a probability by applying the sigmoid function. So we would look at theta transpose x, and we would apply the sigmoid to obtain the following expression. In binary classification, we are going to do the same, except now we're going to, so we will define a model. Well, in the multi-class setting, our model, instead of outputting, so here f outputs a single probability. Now, in the multi-class setting, we're going to output k probabilities, and the probability of each class k is again going to be the softmax of x when we take the dot product of x with some set of weights theta sub k, where we have one set of weights for each possible class. So in other words, given an input, our model, its set of parameters is k times its set of parameters are k instances of theta. So in logistic regression, theta was simply the set of d-dimensional real numbers, and now the set of parameters for our multi-class model is going to be k times this set of parameters. So we're going to have one vector of parameters per class. Then, given an input x, we're going to compute a score for each class by multiplying it with its parameter theta. So each class will have a score that's theta k times x. And then we will simply normalize the scores and convert them into a probability by applying the sigmoid, by applying the softmax function that we saw earlier. And this gives us the following expression. And this is going to be the definition of our softmax model. And again, I want to highlight that this expression is slightly overparameterized. We can multiply the top and the bottom of the previous expression by the same number to obtain an equivalent probability, an equivalent set of probabilities. And so in practice, in softmax, with the softmax model, it is common to assume that one set of weights is fixed to 0. And now these two, now we have defined our model, and in order to define an algorithm, we need to define an objective and an optimizer. And for the objective, we're going to again derive this objective from a probabilistic perspective. Just like we did for logistic regression, we're going to use our softmax model to parameterize a probability distribution as follows. So here we're going to again interpret each component of the softmax function as a probability, because it's between 0 and 1. It's between 0 and 1, and all these components sum to 1. Therefore, our softmax function gives us a valid vector of probabilities, and we can define a probabilistic model that is a probability function where y takes each of these k classes, and we assign the probability of the kth class to be this model. This can also be seen as parameterizing what is called a categorical distribution. A categorical distribution is an extension of the Bernoulli. The Bernoulli distribution, in the Bernoulli distribution, the variable in question that follows the Bernoulli distribution can take one of two possible values, and in a categorical distribution, it can take a number of k possible values, and we're parameterizing each of these by the following expression, by this expression here. So now this defines a probabilistic model over the k possible values that y can take. And again, we can apply the principle of maximum likelihood to obtain a training objective, which looks as follows. Again, this is simply the probability of the training set under our model. And now by optimizing for this set of parameters theta, we have an algorithm called Softmax Regression. And again, we can perform this optimization using gradient descent. This is how it's typically done. And as in logistic regression, the term regression here is a misnomer. This is actually a classification algorithm. I'm not going to implement softmax regression from scratch, but you can see here the definition of softmax regression. You can see here how we can apply softmax regression by calling the implementation in Scikit-learn. So in Scikit-learn, actually, softmax regression is part of the logistic regression class, except that we have to specify that it's multi-class. And now we can fit the model on our iris dataset. This is now the full dataset with the 3 types of flowers. We can generate predictions from this model. And now I can visualize the decision boundaries and the partition of the space, and they take the following form. So here we have again a hyperplane that separates the setosa flowers from the rest, and now we're also separating the two other classes through this line, which is quite reasonable given the data that we have. And again, you should notice that these are straight lines, and softmax regression is also a linear model in the sense that it finds a linear decision boundary. Summarizing what we saw, softmax regression is an algorithm for supervised learning and specifically for classification that fits a model that is parameterized by a softmax function and which looks for linear decision boundaries between the data. Its objective function, we can call it the softmax loss, but this is a special case of the log likelihood, and it's typically optimized using gradient descent. And we can interpret it from a probabilistic perspective as parameterizing a categorical distribution.